Hello scholars, welcome to another Smash Jam series, and today we'll be smashing the topic quantities, units and dimensions in the subject physics, jam physics. So before we smash this topic, I'd like to take you down quantities, units and dimensions. I want to explain to you what quantities, units and dimensions, the basic things that you need to know, all right, so that it gives you an edge on solving different questions. Now, first of all, I'd like to start with quantities. What is a quantity? What are quantities? What's a quantity? Now, a quantity is the property of a body or substance that can be measured. All right? That can be measured. For example, area can be measured, volume can be measured, mass can be measured, all right, and so on and so forth, all right. So a quantity is the property of a body or a substance that can be measured. Area can be measured, volume can be measured, mass can be measured. Now we have two types of quantity. We have fundamental quantity, or let me say fundamental quantities, and derived quantities. Fundamental quantities and derived quantities. Now, fundamental quantity, what is a fundamental quantity? Fundamental quantities are independent, all right? They are the independent quantities. They do not depend on other quantities, all right? They are independent of themselves. They are, let me use the word, they are boss. Okay, they are the boss of themselves. Let me use that word. I guess you understand it like that. All right. So the first fundamental quantity we are going to look at is mass. All right. Now mass is measured in kilogram. All right. Mass is measured in kilogram. All right. Abbreviated as kg. All right. Now the next one I'm going to look at is length. Length is measured in meter. Length is measured in meter, abbreviated as m, small letter m. Now the third one we're going to look at is time. Time is measured in seconds. All right, in seconds. All right, abbreviated as s. And then the fourth one we're going to look at is electric current. Electric current, all right, is measured in ampere. Electric current is measured in ampere. Another one we're going to look at is temperature. Temperature is measured in Kelvin. It is abbreviated as K. Temperature can also be measured in degrees Celsius and also in degree Fahrenheit, but the standard unit is Kelvin. All right, the system international unit is Kelvin. So temperature is measured in Kelvin. Now, another one we're going to look at before we go into derived quantity. Another one we're going to look at is amount of substance. Amount of substance. Amount of substance. Now, amount of substance is measured in mole. All right, it is abbreviated as MOL. All right. Now, another one we're going to look at is luminous intensity. Luminous intensity. Luminous intensity is another fundamental quantity, and it is measured in candela. All right, abbreviated as CD. Right, luminous intensity is measured in candela, abbreviated as CD. Now we're going to look at derived quantities. Now derived quantities, of course, they are dependent. They are the dependent quantities. All right, they depend on other quantities. They depend on the fundamental quantities to exist. For example, area. Area is a derived quantity, all right, because it takes length times breadth, and length is a function of meter, breadth is a function of meter, meaning the unit of length is meter, the unit of breadth is also meter. So they come together, meter times meter, that gives us meter squared. All right, so area is a derived quantity and it is measured in meter squared. All right, now let's look at another one. Volume. Volume is a derived quantity, and volume is length times breadth times height. Length measured in meter, because length is measured in meter. Breadth is also in length, measured in meter. Height is also in length, although a vertical length, measured in meter. That gives you meter to the power of 3. All right. We have density. Now density is mass over volume. Density is mass over volume. So mass is measured in kilogram, volume is measured in meter cube. All right. So it means that the unit is kilogram per meter cube, or you can write it as kgm to the power of -3. All right. So we have various derived quantities like velocity, speed, all right, and so on and so forth. Force, all right, those ones are derived quantities. It takes fundamental quantities to be combined, all right, to give you a derived quantity. So derived quantities are dependent, fundamental quantities are independent, and these are all the fundamental quantities we have. So now let's move next to dimensions. All right, we've looked at units. Now units are yardstick by which quantities are measured. All right, so the mass of a body is measured in kilogram. We cannot just say his mass is 50. You have to say his mass is 50 kilograms, and that's what tells us that, oh, you're talking about his mass. All right, you can just say his mass is 50, but you are supposed to put the unit, because the unit is the yardstick by which that quantity is measured. So you say his mass is 50 kilogram. All right, so we've looked at units, all right, stylishly. After looking at the quantities, all right, side by side, we looked at the quantity with the units. So now let's go to dimensions. Let's go to the next phase of dimension. Let's see how we can get the dimensions of different quantities, and move on to smashing jam questions in quantities, units, and dimensions. So moving on to dimensions. Now dimensions actually show the relationship between physical quantities. All right, dimensions. Now for us to find the dimension of a physical quantity, we have to understand that we use mass, which is measured in kilogram. It is represented with capital letter M. We use length, which is measured in meter, and it is represented with capital letter L. And then we use time. Time is measured in second, and it is represented with capital letter T. So if you know this, your problem has been solved. All right, if you just understand that to get the dimension of a quantity, we need the mass, length, and time, 50% of your problems have been solved in understanding how to get dimensions. All right, now let's get the dimension of the following quantities. Find the dimension of the following quantities. All right, so let's look at volume, let's look at density, let's look at force, and then let's look at work. All right, now for you to find the dimension of a quantity, is either you know the formula or you know the unit. Now, not just knowing the unit, you must know the kgms system units of that quantity. All right, now let's start with the first one. The first one is volume. Now volume is length times breadth times height. Volume is length times breadth times height. All right, length is measured in meter, volume is measured, breadth is measured in meter, height is measured in meter. So meter times meter times meter, that gives us meter to the power of 3. All right, you can also automatically know that the unit for volume is meter cube. So how we know the unit now, we cannot get the dimension. Now meter is from what? It's from length. All right, because length is measured in meter. So meaning that the dimension is going to be L to the power of 3. All right, so the dimension for volume is L to the power of 3. Now let's look at the next one. Let's look at the next one. We have density. Now is either you know the unit of density or you know the formula. All right, now density is mass over volume. Density is mass over volume. Mass is measured in kilogram, volume is measured in meter cube. So it means that the unit of density is kilogram per meter cube, which you can also write as kgm to the power of -3. All right, now that we know the unit, we can get the dimension. So the dimension is going to be what? Kg is from mass, that's capital letter M. So it's going to be capital letter M. Meter is from length, that's capital letter L to the power of -3. All right, so the dimension for density is ml to the power of minus 3. Let's go ahead and look at the dimension for force and work. Now, force is actually measured in Newton, all right, but we can't use Newton as a broken down unit to get the dimension for force. We need the kgms unit system to be able to get the dimension for force. Now, we will have to go to the formula of force so we can get that. Now, force is mass times acceleration. Force is mass times acceleration. All right. So mass is measured in kilogram. Acceleration is measured in meter per second squared. All right. So kilogram times meter per second squared, that gives us kgms to the power of minus 2. Kgms to the power of minus 2. All right. So now we have this. Now we can now get the dimension. So the dimension for force is going to be kg is from mass. That's capital letter M. Then meter is from Mr. Length. That's capital letter L. And then S is from Mr. Time, that's capital letter T to the power of minus 2. So the dimension for force is mLT to the power of minus 2. Now let's go ahead and find the dimension for work. So we want to find the dimension for work. Now, work is measured in joule. Alright, work is actually measured in joules, abbreviated as capital letter G. But we need the kgms system to be able to get the dimension for work. All right, we don't need this. Now we'll have to go to the formula. So work is force times distance. Force, we just got now, is measured in kilogram meter per second squared, multiplied by distance is measured in meter. So this meter multiplied by this meter gives us meter squared. So it becomes kg m squared, because I'm multiplying m in two places, s to the power of minus 2. So finally, what will be the dimension? Now, kg is from Mr. M, which is mass, capital letter M. M is from Mr. Length, so that's L to the power of 2. And S is time, that's T to the power of minus 2. So this tells us that the dimension for work is ml squared T to the power of minus 2. Now, let's go further to smashing jam questions on quantities, units, and dimensions. The correct unit of energy density is A, kgm to the power of 3, V to the power of minus 2, B, kgm squared, s to the power of minus 2, c, kgm to the power of minus 1, s to the power of minus 2, d, kgm to the power of minus 1, s to the power of minus 2. Oh, I might not be able to call these options off, but let's solve these questions. So now the correct unit of energy density is, now what's energy density? Energy density is simply energy over volume. All right, energy over volume. Now, energy, of course, is measured in joules. Volume, all right, is measured in meter cube. But we don't need these joules. All right. Now we know that what work is also measured in joules. And what's the formula for work? Force times distance. So we could also relate the formula for energy as force times distance. So this is going to be force now. So this is force times distance over volume. So force times distance, force is measured in kilogram meter per second squared, which is from mass times acceleration. All right, multiplied by distance is measured in meter over now velocity over volume, measured in meter cube. All right, so this m and this m, that gives us what? Kgm squared s to the power of minus 2 over m to the power of 3. So now what are we going to have here? Now this m squared is going to take away m squared here, so you're going to be left with 1m here. All right, so this is going to be what? Kgs to the power of minus 2 over m. Now you can bring this m up here, but if this m should come up here, it comes as an inverse of 1. All right, so if it's coming as an inverse of 1, so it becomes kgm to the power of minus 1 s to the power of minus 2. Now some persons would have asked me, if this was kgs to the power of minus 2 over m squared, what will it be? If it's coming up, it's going to become kgm to the power of minus 2 now, s to the power of minus 2. All right, but in this case the power here is just 1, so if it's coming up here, it becomes minus 1. So the correct unit of energy density is simply kgm to the power of minus 1 s to the power of minus 2, which is option D. The unit of moment of a couple can be expressed in, now we're giving these options. Now what is moment of a couple? Moment of a couple is simply force times perpendicular distance. Force times perpendicular distance. Now, force is measured in Newton, perpendicular distance is measured in meter. So Newton times meter, that gives us Newton meter, right? So the unit for moment of a couple is Newton meter, and that will be option A. Force, torque, current, power. I, which is force measured in Newton. I, torque, which is measured in Newton per meter. Alright, current measured in ampere, and power measured in watts. Which of the above are the correct SI units of the quantities indicated? Now the first one is force. Of course, force is measured in Newton. Alright, force is measured in Newton. Torque, now torque is force times distance. Alright, force times distance. So it's supposed to be measured in Newton meter, because force is measured in Newton, distance is measured in meter, and current is measured in ampere, power is measured in watts. So the only one that is not correct is this guy, torque. The only one that is given to us here, which is not correct, is this guy, which is II. So they say which of the above are the correct SI units of the quantities indicated. So we have it that only III and IV are correct. So which of the options has that? That is option D. So this is the answer. Which of the following is the dimension of pressure? Which of the following is the dimension of pressure? Now I told you, is it that you know the unit of a quantity to get the dimension, or you know the formula? So let's assume we don't know the unit. So what's pressure? Pressure is force over area. Pressure is force over area. And force is itself is mass times acceleration. Mass times acceleration over area. Right, area is length times breadth, which this is measured in meter, this is measured in meter. Mass is measured in kilogram, acceleration is measured in meter per second squared. So let's multiply. So kilogram times this gives us kg ms to the power of -2 over meter times meter, that gives us meter squared. Of course, we know that 1 meter is going to eliminate 1 meter from here, and then we're going to be left with 1 meter. So this is going to be kg s to the power of -2 over m. All right, now this goes up here. You see that it becomes kg m to the power of -1, right, s to the power of -2, because this can go up here. All right, so if it's going, it becomes an inverse. So now that we have gotten the unit, we can now get the dimension. This is kg. Kg is from Mr. Mass, which is capital letter M. All right, m is from Mr. Length, all right, which is represented with capital letter L to the power of -1, and then s is from seconds, is from time, which is represented as capital letter T, that's T to the power of -2. So this is the dimension for pressure. So which of these options has this? That should be option A. So this is our answer. So the dimension is ml to the power of -1, T to the power of -2. The equation P to the power of x, V to the power of y, T to the power of z is equal to constant is Charles' law when the following conditions are given in the options. Now, before we can solve this question, we have to understand what is Charles' law. Now, Charles' law states that the volume of a given mass of a gas is directly proportional to the temperature, provided that pressure remains constant. All right, directly proportional or directly varies as the temperature. All right, provided that the pressure remains constant. So this is going to be introducing a constant. This is going to be V is equal to KT. All right, let's make our constant the subject of the formula. All right, so making our constant the subject of the formula, divide both sides by T. K is going to be equal to V over T. That's dividing both sides by T here. K is going to be equal to V over T. Now, this can also be written, I can split this into K is equal to V multiplied by 1 over T. Now, V times 1 is TV over the same T. All right, I'm going somewhere here. All right, now 1 over T, according to the law of indices, can also be written as what? Also written as T to the power of -1. So this is going to be K is equal to VT to the power of -1 when you multiply this and this. All right, so now we can do something, because while giving this, all right, we are giving this is equal to constant, and we have this. Now we can do something here. We can manipulate this to be equal to K is equal to P to the power of 0 VT to the power of -1. P to the power of 0 is T1, Anything to the power of 0 is still 1. 1 multiplied by vt to the power of minus 1 is still vt to the power of minus 1. You're just trying to manipulate because you need to get an answer. Alright? So now let's compare this and compare this. So we have p to the power of x, v to the power of y, t to the power of z is equal to constant. And then we also have that from here, p to the power of 0, v and then t to the power of minus 1. Now I want you to know that v here has an invisible 1 on top because v to the power of 1 is tv. Alright, so let's put 1 there is equal to constant. Now if we compare both sides, you find out that x is equal to 0. Compare this and this, you find out that y is equal to 1. And then compare this and this, you find out that z is equal to minus 1. Alright, so this is going to be Charles' law when what? So we have x is equal to 0, y is equal to 1, and z is equal to minus 1. And which option has that? Has what we are looking for. That is option B. Option B. So when x is equal to 0, y is equal to 1, z is equal to minus 1, this will represent Charles' law. At what respective values of x, y, and z would the unit of force, the Newton, be dimensionally equivalent to m to the power of x, l to the power of y, and t to the power of z? Now, force is what? Force is mass times acceleration. Mass times acceleration, that's force. Now mass is measured in kilogram, acceleration is measured in meter per second squared. Multiply them together, that gives you kg ms to the power of minus 2. All right, kg ms to the power of minus 2. Now mlt is the way, is by the form which dimensions are represented. All right, so we have to find the dimension of this. Now what's the dimension of force? Kg, all right, is represented as capital letter M. Meter is represented as capital letter L, and second is represented as capital letter T to the power of minus 2. All right, so we're going to compare this and compare this. So we have m to the power of x, l to the power of y, t to the power of z. All right, and we also have m, l, t to the power of minus 2. Of course, there's an invisible one here and there's an invisible one here. All right, so if you compare this and this, you find out that what? X is equal to 1, y is equal to 1, and then z is equal to minus 2. Z is equal to minus 2. So which of these, because it said equivalent to this respective value of x, y, and z. So these are the respective value of x, y, and z, which is 1, 1, minus 2. So which of these options has 1, 1, minus 2? That's option B. So option B is our answer to this question. The physical quantity that has the same dimensions as impulse is which of these? Now I want you to know from today that impulse has the same unit and dimension as momentum. Now let's check that. Impulse is force times time. Momentum is mass times velocity. Force is measured in kilogram meter per second squared times time, which is measured in seconds. All right, and then this is what? This is mass times velocity. That's kilogram times ms to the power of minus 1. Now this is s to the power of minus 2. This is s to the power of 1. So when they come together, we have kg ms to the power of, applying the law of indices, minus 2 plus 1. So it becomes kg ms to the power of minus 2 plus 1. That gives us minus 1. All right, now this is kg ms to the power of minus 1 also. Now there are dimensions automatically for this. Now you are going to have m, that's kg, small letter m, l, then s, t to the power of minus 1. This also is going to be m, l, t to the power of minus 1. So if you look at it very well, you find out that their dimensions and their units are the same. All right, their dimension and their units are the same. So momentum and impulse have the same unit and dimension. The dimensions of electromotive force is, now for us to easily get our answer, I want to remind you of the formula that says W is equal to QV. W is equal to QV. Now V is the electromotive force, which is also known as voltage. W is work and Q is charge. W represents work, Q represents charge, electric charge, and then V represents EMF or voltage. All right, or voltage. Now let's make V the subject formula from here. Make V the subject formula. You are going to have what? Divide both sides by Q, W over Q. So it's from this that we can get the dimension, or first get the unit for this, then we can now easily find the dimension. Now let's come to this side. Now V is equal to work done over charge. Now work done itself is what? Force times distance, and charge is what? Current times time. Q is equal to IT. Do not forget that formula. Q is equal to IT, or capital letter Q is equal to IT, any of them. All right, current times time. All right, current times time. Now this force is measured in kg ms to the power of -2 multiplied by distance is measured in meter over, now current, let's leave it as I. All right, current is actually measured in ampere, but you are seeing I here. All right, from the options you are already seeing I, so you don't need to represent this as ampere. Multiply by seconds, because time is measured in seconds. All right, now what's going to happen is that we're going to bring these two up. All right, now it becomes this m and this m, it becomes kg m squared s to the power of -2 over is, capital letter is. Now these two can come up. When they come up, it becomes kg m squared s to the power of -2 multiplied by I to the power of -1 s to the power of -1. All right, that's bringing them up. All right, we can take them up, but they become inverse. Now this s and this s are going to come together, all right, according to the law of indices. So it becomes kg m squared s to the power of -2 plus -1. All right, you're adding the power, then I to the power of -1. Now this becomes kg m squared s to the power of plus times minus. That gives you -2 -1, I to the power of -1. Now coming here, this is kg m squared s to the power of -2 -1, that gives us -3i to the power of -1. So automatically, what is going to be the dimension? So the dimension for this is going to be kg is from Mr. Mass, that's represented as capital letter M. Meter is length to the power of 2. Then s time, t to the power of -3. Then I to the power of -1. So the dimension for electromotive force, is ml squared t to the power of -3, I to the power of -1. So which of these options has this? All right, which of these options has this? That is option A. So option A is our answer. ml squared t to the power of -3, I to the power of -1 is the dimension for electromotive force. The values of x, y, and z respectively in the expression m to the power of x, l to the power of y, t to the power of z for the universal gravitational constant G are. Now you'll be asking, where does this universal gravitational constant G comes from? It comes from Newton's universal gravitational law that states that the force of attraction between two masses is directly proportional to the product of the masses of the bodies and inversely proportional to the square of the distance between them. Bringing all this together, I have this over r squared. All right, I have that F is directly proportional to m1 m2 over r squared. Now if I introduce a constant, that constant is called Newton's universal gravitational constant, which is G. So this becomes F is equal to G m1 m2 over r squared. All right, now for us to be able to get the dimension of this G, all right, so that we can find the values of x, y, and z respectively, let's make G the subject of formula. So let's make G the subject of formula. So we have F is equal to G m1 m2 over r squared. All right, I can put over 1 here, cross multiply. All right, so this times this gives you G m1 m2 is equal to this multiplied by this gives you fr squared. Now make G the subject of formula, divide both sides by m1 m2. So G is going to be equal to fr squared over m1 m2. Now let's continue. Now, so G is going to be equal to, the unit for force is Newton, all right, but the broken down kgms system unit is kilogram meter per second squared multiplied by, this is r. All right, this r here is measured in meter because it's a distance. Now, but you're having r squared here, so it's going to be not just m but meter squared, m squared, all right, over, now this is mass 1 measured in kilogram times another mass 2 also measured in kilogram. All right, so this becomes what? Now you're going to find out that kg eliminates kg here, and then you're going to be left with what? This m, and this is an m to the power of 1 here, there's an m to the power of 2 here. So it becomes what? G is equal to m to the power of 3 s to the power of minus 2 over kg. I can make this kg come up here, alright, because I don't want it to be down here, because I need to put it in form of dimension so I can get the value of x, y, and z. So I can bring it up here. If I bring it up here, it becomes kg to the power of minus 1, m to the power of 3, s to the power of minus 2. Alright, so in form of dimension, it is going to be m to the power of minus 1, l to the power of 3, t to the power of minus 2. Alright, so this is the dimension for universal gravitational constant. So let's compare this to this. So we have m to the power of x, l to the power of y, t to the power of z. Let us compare it with m to the power of minus 1, l to the power of 3, t to the power of minus 2. Alright, so comparing both sides, you find out that what? X is equal to 1. That's compare, sorry, not 1, minus 1. Alright, compare this and this. Now you find out that y is 3. Alright, and z is equal to what? Minus 2. Right, minus 2. So the values are 1, minus 1, minus 1, 3, and minus 2. Minus 1, 3, and minus 2. So that should be option B. Minus 1, 3, and minus 2. Alright, so the values of x, y, and z are minus 1, 3, and minus 2 in the expression for this, for the universal gravitational constant G. The equation p to the power of a, v to the power of b, t to the power of c is equal to constant reduces to Charles' law if, now we've solved this question before. You can pause this video and try it out yourself. Although we're not giving ABC, we're giving X, Y, Z, but you can solve this question. But let me solve it. Alright, now Charles' law states that the volume of a given mass of a gas is directly proportional to the temperature. Introducing the constant, you have V is equal to KT, and then K is going to become what? By the time making the solving formula, V over T, which you can also write as Vt to the power of minus 1. Now, there's a P here, so I can manipulate this to be K is equal to P to the power of 0, V to the power of 1, T to the power of minus 1. P to the power of 0 is still 1, because anything to the power of 0 is 1. 1 times all this still gives me this, alright? So comparing this with this, compare this. Let's compare P to the power of A, V to the power of B, T to the power of C is equal to constant, and also compare P to the power of 0, V to the power of 1, T to the power of minus 1 is equal to constant. Let's compare. You find out that A is equal to 0, B is equal to minus 1, and then C is equal to minus 1. So our answer is 0, 1, and minus 1. 0, 1, and minus 1. That is option B. We have option B. Alright, so the values for A, B, and C are 0, 1, and minus 1, which is option B. The dimensions of power are the dimensions of power. Now, is either you know the unit, like I said, or you know the formula. Now, the unit for power is watts, but that's not the broken down kgms system unit we need to get the dimension. So what do? Let's go to the formula. Now, power is work done over time, or let's just say work over time, to be brief. Now, work is force times distance. Time is time, which is measured in seconds. Alright, so now this becomes what? This as a whole becomes that power becomes force times distance. Force is measured in kilogram meter per second squared. That's mass times acceleration times distance measured in meter over time measured in seconds. So this m and this m comes together. We are going to have kgm squared s to the power of minus 2 over s. This s can come up, alright, as an inverse. So it becomes kgm squared s to the power of minus 2 multiplied by s to the power of minus 1. Alright, so this and this can come together, alright, according to the law of indices. So it becomes kgm squared s to the power of minus 2 plus minus 1. So it becomes kgm squared s to the power of minus 2 plus and minus 1. So this becomes what? Kgm squared s to the power of minus 3. Because minus 2 minus 1 gives us minus 3. So let's finally get the dimension. So the dimension is going to be m, capital letter M, from kg, meter, that's going to be L squared, and then seconds, that's going to be time, t to the power of minus 3. So the dimension is going to be ml squared t to the power of minus 3, which is option A. So option A gives us our answer. What is the dimension of moment? What is the dimension of moment? Now, moment is force times distance. Alright, moment is force times distance. Force measured in kilogram meter per second squared, which is mass times acceleration. Distance is measured in meter. Alright, so multiply this and this, you have kg m squared. That's the m and m gives you m squared. Then you have s to the power of minus 2. So automatically the dimension becomes capital letter M, kg, meter, that's from Mr. Length, to the power of 2, seconds, that's time, to the power of minus 2. So the dimension for moment is ml squared t to the power of minus 2. ml squared t to the power of minus 2. Alright, we can see clearly that there is no option there, but this is the answer, ml squared t to the power of minus 2. So that will be all for this Smash Jam series. Now, make sure you like, subscribe, share and comment on this video. And do well to hit the notification button so when I upload a video, you get notified. Thank you.